All right. Hello, world. This is CS50. My name, again, is David Malan, and
I'm Brian Yu.
We are back for the second of two live filmings today, wherein we're producing CS50's new course, Fundamentals of Artificial Intelligence, with CS50's own Brian Yu. If you tuned in earlier today, this is going to be more of the same course, but a different topic, the second lecture of the course. If you're joining us anew, perhaps the best FAQ, frequently asked question, we can answer is, Brian, how is this course different from CS50 AI?
Right, so CS50 already has a course about AI, Introduction to Artificial Intelligence with Python. That course is geared towards students who have a little bit of a programming background already. Maybe you've taken CS50 or programmed in Python before and are interested in learning how you can write code to program your own AI. This course is designed to be, that we're filming today, is designed to be a little bit more introductory. It's designed for audiences, even if you don't have a programming background before, you can still learn about how AI works, what's really going on with these technologies, what their strengths and limitations are. So regardless of whether you come from a background of having prior coding experience or not, you'll hopefully find something you can learn in this class too.
So you can register for this course later this year via edx.org, as well as CS50's own website. The videos will ultimately be on YouTube as well once we've edited them, and the assignments will be available at that time too. In the meantime, during the next hour or two while we're filming this lecture, if you have any questions, feel free to ask in the chat if you're watching this indeed live. I'll do my best to field some of them. You're all welcome to answer each other's questions, and I'll do my best to relay some of the questions by raising my own hand here in the theater to Brian himself. So without further ado, this is CS50.
Welcome back, everyone, to Fundamentals of Artificial Intelligence. So last time, we took a look at how we can get AI to play games. We looked at techniques we can use and algorithms we can use to allow AI to be able to look through a game tree and figure out what the optimal move was. And eventually, we made our way to the world of machine learning, the idea that computers can get better at a task by learning, whether it's learning from data or learning from experience. And today, we're going to dive even further into this world of machine learning, in particular, looking at how we can use machine learning to allow our AI to make predictions. So what is prediction all about? The idea behind predicting is that we want to give our AI some information. We want the computer to be able to learn the underlying patterns in that information and use what the computer has learned to then go forward and make some predictions. And computers make predictions all the time. Computers are predicting traffic conditions on the road. Computers are predicting what kind of music or movies that you might enjoy. Computers are predicting whether an email is going to be important to you or whether it's a spam email. Computers are predicting what kinds of friends you might be interested in following on social media. So lots of opportunities in different ways that computers try to predict things. And ultimately, when we're predicting things in the real world, we have to deal with the complexities of the real world. The real world has a lot of variables, has a lot of uncertainty. And so in some ways, it's a new challenge compared to what we were doing last time when we were dealing with games that had very well-defined, usually fairly simple rules that were just easy constraints that computers could work within. So today, we're going to be taking our AI, moving our AI from the world of games into the real world, and seeing how AI can engage in some predicting. So let's go ahead and bring our AI into the real world. Here's our little AI here. And let's imagine, for example, that we're interested in growing some plants. So our AI is growing some plants. And one thing you might notice is that plants will grow more when they have more sunlight, for example. So if there's a lot of sunlight, then we might expect that these plants are going to grow a little bit more. And maybe we're interested in trying to predict how much these plants are growing, just to take a very simple example. So a very basic prediction task in this sense would be trying to say, let's assume we know how much sunlight there is measured in some units. What we might be interested in trying to predict is we might want to predict how much our plants are going to grow, and therefore predict some number that represents how much those plants are going to grow. Now, without any additional information, there's no real way that an AI would be able to do this. Without knowing information, we would just have to guess how much we think that plants are going to grow. But ultimately, what we can do with artificial intelligence is try to learn from data. That if we had some data about existing plants, and we knew how much sunlight those plants got and how much those plants grew as a result, then we could try to model the relationship between those two variables and try to understand how changes in the amount of sunlight that a particular plant receives affects how much that plant grows. Ultimately, this kind of problem applies not just to plants, it applies to lots of things. But this kind of problem is what we call a regression problem. A regression problem is where we're trying to predict some kind of a number. And in this case, the number that we're trying to predict has to do with how much plants are growing. But there are lots of other applications that you might imagine where regression might be useful. For example, imagine that you're running a business, and you might care to know, depending on how much money you spend on advertising, what impact that's going to have on your sales. The amount of sales is some number that you're trying to predict based on a particular input variable. And there are other examples we could imagine too. Maybe you're interested in knowing how the fuel efficiency of your vehicle is affected by how fast that vehicle is moving. Or there may be health problems that we might consider too, where you might measure the amount of exercise you do and see what effect that has on your blood pressure. Anytime we have numbers that we're trying to relate to each other, where we want to see how some number as input affects some number as output, we could try to treat that as a prediction problem. That if I know what the input number is, do I have the ability to predict what the output number is going to be? And there are a few different ways we could try to approach this. But let's go back to our example of plants and sunlight and how much those plants are growing and see if we can visually try and understand how we might try to make some predictions based on some data. So we'll go ahead and take some data and plot this data on 2 dimensions on a graph of some sort. Along one dimension, we'll imagine that this dimension represents how much sunlight the plant is getting, and this dimension here, the y dimension, is representing how much the plants are growing. And you can see that each of these data points represents data about one plant, for example, that we might be able to feed in as input to our machine learning process, representing for one particular plant, here is how much sunlight that particular plant got, and here is how much that plant grew as a result. And so if I had all of this data laid out visually like this, hopefully we can see that there's kind of a positive correlation here, that the more sunlight a particular plant gets, the more that plant is ultimately going to grow. And we could try to draw a line that represents the relationship between these 2 variables. And so the line might look something like this. It seems to approximately, it doesn't go through all of the points. In fact, it doesn't go through any of them in this particular case. But it approximately follows the same shape as the data that we're looking at. And so maybe this could do a reasonable job at trying to predict how much these plants are going to grow. Of course, this isn't the only line that we could have drawn. We could have drawn a different line. Maybe this one looks pretty good. Or we could move the line around a little bit more. Maybe that one looks better. It's hard to tell. Or maybe the original one was actually the best one of all. It's a little bit difficult to know unless we can start to be a little bit more mathematically precise about how good a particular line is. And so when we're engaging in machine learning, when we're trying to get our AI to be able to learn something, what we need is some kind of a metric, some way to evaluate how good or bad the predictions that we're making really are. And in the world of machine learning and artificial intelligence, typically the way we'll do that is via something called a loss function. So what is a loss function? A loss function is going to describe how good or bad our predictions are. Because in the end, we're not going to be able to predict everything perfectly in reality. What we're building is what's called a machine learning model. And a machine learning model is a structure that we're creating that is going to take in some input data and then try to make some predictions, but those predictions aren't going to be perfect. And the loss function is going to allow us to measure how good or bad those predictions are. So let's take a look at an example of how we might actually try to measure the loss, measure how good or bad our particular predictions are. So for now, the machine learning model that we're going to try to build is really just going to be a line representing the relationship between 2 variables. But later today, and as we go through this course, we'll start to see that we can start to build some more sophisticated machine learning models as well. But our model for now is very simple. It's just a single line trying to define the relationship between 2 variables. And ultimately, what the line is trying to do is it's trying to make some predictions based on data. So here's a real data point representing some amount of sunlight that a plant received and how tall that plant grew. And what we're going to say is we're going to give that point a name. We'll call that y, for example, the output of some function. And our line made some sort of prediction for that data point. Given this amount of sunlight, our line made some kind of prediction for how much growth we thought that plant would see. And that's a slightly different point. It might not be exactly the same. This point we usually describe as the letter y with a little hat symbol on top of it. We call that y hat. So what you're looking at visually here is y. This is the real data point, some real piece of data collected from some real plant. And this line represents our machine learning model, which made a prediction. This is our prediction y hat, which is a little bit different. It's not perfect, but hopefully it's pretty close. And what we'd like to do now is quantify how good or bad that particular guess was. So how could we do that? Well, there are a few different metrics we could use, but one metric is just looking at what is the distance between these two values, the distance between y and y hat. This is what we might call the absolute error. The absolute error is just what is the difference between these two values, what we predicted, and what the actual value turned out to be. And the way that we could calculate that mathematically is we could take one value and subtract the other. So in this case, we're taking y hat, and we're subtracting y. And these bars on either end means we're going to take the absolute value. And if you don't remember what the absolute value is, the idea there is that if the number is negative, we're just going to turn it into a positive number. So the absolute value of -5 is just +5. And the reason we're doing that is because when we're trying to measure the error, in many cases, we don't really care in which direction the error happens to be. If our prediction was a little bit too low or our prediction was a little bit too high, what we care about is how far away were we from the actual value. Maybe we don't care so much about was it too far below or was it too far above. If you did, you could construct a different way of trying to measure the error. But the absolute error is one common way of just seeing what is the difference between what our machine learning model predicted and what the actual truth is. Another popular way to measure error is the squared error. So in the squared error, instead of just taking the literal distance between the prediction and what the true value is, we take that distance and then we square it. We multiply it by itself. And what that does is it has the effect of magnifying larger errors. So if the absolute error was 1, then the squared error is still 1. But if the absolute error was 2, the squared error grows to 4. If the absolute error was 3, the squared error is 3 squared, or 9, and so on and so forth as the numbers get bigger. And so bigger and bigger errors have the effect of meaning even larger squared errors, which penalizes large errors even more. And this tends to be a pretty popular choice because in reality, hopefully if our machine learning model is good, then you would expect that smaller errors are more likely than bigger errors. And so you want to penalize those bigger errors even more. And it has some other nice mathematical properties too. But when we're evaluating how good our machine learning model is, usually we're not just going to evaluate it on one data point. One data point it's hard to really make a lot of conclusions about. Ideally, we'll have collected a bunch of data on different plants and different environments and used all of that to try and make some predictions. So rather than just one value y and one error that we're looking at, we might have multiple different points of data, and we're going to look at the error for all of them. Say, here's what our model predicted for each of these two other points. And each one of those has some error too. And so when we're trying to evaluate how good our machine learning model is on all of this data, one thing we could calculate is the mean squared error. So we take that squared error, the distance between these two values squared or multiplied by itself, and we take the mean or the average across all of the data points. And by doing that, the mean squared error will hopefully give us a pretty good sense for how good or bad our predictions happen to be. If the mean squared error is really high, well then the thing we predicted probably not such a very good machine learning model because it's producing a lot of error. If the mean squared error is lower, then in general that tends to be better. And that gives us a very mathematical metric that we can use when trying to figure out which line is the best line. There are mathematical techniques we can use to try and essentially optimize. And when we're trying to figure out what line it should be, we can pick the line that minimizes the mean squared error, that finds the smallest possible mean squared error. And so hopefully that's going to be the model that's going to be the most predictive. So that's one way that we can engage in this task of regression, trying to predict a number based on some other number that we're using as input. Now, so far, we've primarily been looking at cases where there's one input variable and one output variable. The input variable was sunlight, how much sun did the plant get, and the output variable is growth, how much did that plant grow as a result. But it doesn't need to be limited to just one input variable and one output. For example, you might imagine that there are other factors that can impact the growth of a plant too. Maybe we care not just about how much sunlight the plant received, but we might also want to predict based on how many nutrients are in the soil by doing some quantification of that value too. And so you can imagine multiple inputs trying to predict an output, but ultimately that's going to work the same way. We are going to try and figure out how to predict what this output value is, and we can use the loss function, something like the mean squared error, to say how good or bad was our prediction and figure out what's going to lead to minimizing that mean squared error. So this is one type of value that we might try to predict, trying to predict an individual number. But what else could we potentially try to predict in a machine learning setting? Well, let's go ahead and go back to our AI and back to growing some plants and think about what other things we might be interested in predicting in this case. And one thing we might care about if we're growing some plants is we care about whether or not it's going to rain. Because on days when it rains, maybe that changes what we need to do with the plants. Maybe it changes how much the plants are growing. But it might be useful to us to predict, is it going to rain or not? You might care about this even if you're not growing plants for your everyday life, knowing what clothes to wear outside or whether you need to bring an umbrella or not. Being able to predict whether it's going to rain or not could be something that ends up being quite useful. Now, there are ways that we could frame this as a regression problem. Remember that regression is all about predicting a number. And so conceivably, you could imagine that we predict a number, like predict the amount of rainfall, how much rain there really is. Or if we wanted to, if we don't care about how much rain there is and we just care about whether it's raining or not, we could try just predicting a category. If I had to categorize the day, am I going to categorize it as a raining day or as a not raining day? And so here, we're not predicting a number. We're just predicting a classification, so to speak. And so this is a new kind of problem. A classification problem is where we're not predicting a number. We're just predicting a category. Is today going to be a rainy day or a not rainy day? And so let's take some time now and think about how we could try and train a computer to be able to perform a classification, to be able to predict what category something belongs to. And we'll start by taking a look specifically at the example of rain and how it is that we could try to predict whether or not it's going to rain. And we might think about what factors influence whether it's going to rain. And we could think about them and imagine what they might be. For example, the temperature outside might be one factor that influences whether it's going to rain. Likewise, the air pressure, that probably also has some impact on whether it's going to rain that day or not. How many clouds are in the sky, the cloud cover, that could be something that's relevant too. And maybe also the humidity. Based on the humidity in the air, that might tell you whether it's going to rain too. So all of these pieces of data are what we call features. They are parts of our input data that are going to try to help us predict what the output is. And in order to predict the output well, we need example data of this form, data across our features that will allow us to tell us whether or not it's going to rain. And so the goal then is from all of these features, by knowing the temperature, the air pressure, the cloud cover, and the humidity, we would like to predict whether or not it's going to rain. And again, rather than predict a number like that ranges and is continuous, we're just predicting a category, either yes, it's going to rain, or no, it's not going to rain. So that's essentially what our classification task is all about. It's about taking all of these input features and then trying to predict yes or no, is it going to rain or not? Sorry, brief break to get a drink of water, and then we'll continue. So now we've defined the problem. We're trying to predict some category, like whether it's going to rain or not, based on some input data, like the temperature, the air pressure, the cloud cover, the humidity, et cetera. But now what we need is some algorithm in order to do that, some process that's going to allow us to predict what the classification ultimately is going to be. And it turns out there are a lot of choices for what kind of classification algorithm we might try to use. Let's go ahead and start with a simple one. And we're going to start just by looking at a single variable. Let's imagine that we were trying to predict whether or not it was going to rain just based on one variable, which might be, say, air pressure. So we'll draw a line representing air pressure. And of course, as with before, without any data, we'd have no way of making any kind of prediction. We don't know whether what the relationship is between air pressure and whether it's going to rain, unless we have some example data from real days in the past where we know what the air pressure was, and we know whether or not it rained on that particular day. So let's give ourselves some data to work with. Here's one data point representing some amount of air pressure. You're imagining this is a scale from low air pressure on the left to high air pressure on the right. And this blue dot here will represent a rainy day. So here's a rainy day with a certain amount of air pressure that we have in our existing data set. And let's imagine now that we have another data point. here's a data point here, representing a different day. The air pressure was a fair bit higher. And this red is going to represent no rain. So this was not a rainy day. So we have a rainy day over here with a lower air pressure, a not rainy day over there with higher air pressure. And of course, 2 points it's difficult to make a lot of conclusions about. So let's give ourselves some more data too. So here are some more pieces of data. We have a bunch of rainy days, and we have a bunch of not rainy days, all with a certain amount of air pressure that we can measure. And now imagine that we were asked to make a prediction. We were asked to say, here's a day. We don't know yet whether it's going to rain or not, but here's the air pressure. It falls at this value right there. Can you predict? Is it going to be a rainy day or not? And if you were to look at this visually, what might you guess? Would you guess that it's going to be a blue point, a rainy day, or a red point, a not rainy day? And, well, it's hard to know for sure. We definitely don't know for sure. But one thing we can say is that this point really looks pretty close to this other existing point that's already in our data set. And that other existing point is a red point, representing no rain. And so it's probably a pretty good guess that this point we don't know anything about. If we had to make a guess, maybe we're going to guess that it's also going to be a red point, a not raining point. What we've just done is a very simple classification algorithm known as nearest neighbor classification. And the way that nearest neighbor classification works is we have some existing data set where for each point in our data set we know the values of all of the features like air pressure, for example. And we also have a class or a label. In this case, the class or label is it a rainy day or not? Is it a blue point or is it a red point? And what nearest neighbor classification does is it says, given some new point that we don't know anything about, just find the data point in the existing data set that it's closest to and see what class that belonged to. Is it a blue point or a red point? Is it rainy or not rainy? And based on that, that tells us what our prediction is. So using nearest neighbor classification, if I had another point that was located right here, for example, and I needed to guess, is it a red point or a blue point, we'd find the nearest neighbor. The nearest neighbor is blue, and therefore our prediction is that this one is also going to be blue. And again, this isn't going to be perfect, but it's probably going to be pretty good because we're looking to data that is close to it and using that to make a kind of prediction. We're assuming that there's some general pattern here where it does seem like when the air pressure is lower, it's more likely to rain. When the air pressure is higher, it seems like it's less likely to rain. But of course, in the real world, data is usually not so perfect like this, where all the blue dots are on this side and all the red dots are on this side. The data is going to be mixed around a little bit. You might have blue points surrounded by red points and vice versa. And so the data is going to be a little bit messier. And that leads us to some additional challenges that we need to think about when we're thinking about something like nearest neighbor classification. Imagine the data looked like this, where generally speaking, there seems to be blue on this side and red on that side, but there do seem to be some outliers, a blue point that happens to be over there. What would happen if a new data point came along that was right there? Would you predict that it's red or blue? And the answer might not be obvious. Both could be reasonable guesses. A reasonable person might say, well, this data point looks really close to this other data point. This point is blue, and therefore the one in question is blue as well. But you also might say, reasonably, that it seems like the blue ones are appearing on the left side, the red ones are appearing on the right side. And so if I had to make a guess, maybe I should guess red instead. And so that wouldn't be nearest neighbor classification, because in nearest neighbor classification, we're just looking at the one neighbor that our data point is closest to. And in this case, the one neighbor that our data point is closest to is a blue point, and therefore we'd say that it's a blue point. Instead, we can do something called k nearest neighbor classification. What k nearest neighbor classification is going to do is it's going to say that rather than just look at the one point that it's closest to, look at several points in its vicinity. Maybe look at the 3 closest points or the 5 closest points and essentially have them all vote. If of the 3 closest points, most of them are red, then maybe we're going to say that this point deserves to be red too. And so this is what we call k nearest neighbor classification, where we get to pick the value of k. We could say k equals 3 to say look at the 3 nearest neighbors to make a decision about how we want to classify the point. Or we could say k equals 5, look at the 5 nearest neighbors. Depending on how much data you have, you could choose a different value for how many neighbors you want to look at in order to make a decision about what category something belongs in. So nearest neighbor classification can be quite powerful, and it's also fairly intuitive. It follows from the idea that if I need to make predictions about a piece of data that I've never seen before, well, then I should look at data that is similar to it and use that to try to make a prediction as well. And here we're doing this in one dimension for one variable, just looking at air pressure. but you could imagine that we could reasonably do the same thing for multiple variables too. Remember, we decided there are multiple things that affect whether or not it's going to rain. And so you could imagine that we could plot this in 2 dimensions, say air pressure along 1 dimension, humidity along a 2nd dimension, and I could plot whether or not particular days rained or didn't based on data that I've collected, where for any given day, I know its air pressure, I know its humidity, I know whether it rained or not, and I can plot those in 2-dimensional space, and then do a similar type of thing, that if I have a data point that I've never seen before, I could plot it in this 2-dimensional space, and then say which data point is it's closest to, except instead of along a line, we're working in a 2-dimensional grid. And as we have more and more variables, we can increase the number of dimensions here. If we had 3 input features, not just air pressure and humidity, but we added a 3rd one like temperature, then you could imagine plotting points in 3-dimensional space and looking for what 3-dimensional point is closest to the point in question. And if we had 4 or 5 or 6 or 10 or more different features, then you could imagine 4 or 5 or 6 or 10-dimensional space in which we're plotting things as well. And that might start to seem a little bit confusing, because we're probably used to imagining things in 2D. We're used to imagining things in 3D. But what does 4D or 5D or 10D even mean? It's hard for us as humans to be able to visualize it. But for computers, it's really no different. It's just one additional number that it needs to keep track of and a little more calculation that it needs to do. But from a computer's perspective, the 3rd dimension versus the 4th dimension versus the 5th dimension, it can keep track of that just fine. And so that's something we'll see come up again and again in the world of machine learning, that often we're dealing with many different numbers, not just 2 different numbers that we're trying to compare, but maybe 10 variables that all matter. And so we might care about working in these higher dimensional spaces that are hard for us to visualize them, but to make it easy for us to think about, we can represent them in just a couple of dimensions, in 2 dimensions like this, but you could imagine generalizing that to more dimensions as well. OK, I'll pick up from there. Let me check something quick.
And 2 questions when you get a chance.
So nearest neighbor classification can be used to solve a wide variety of types of problems. So one example of a type of problem that your computers are solving every day is the problem of detecting whether an email is important or whether a particular email is spam. Spam detection is an important task that our computers and our email accounts need to be able to deal with. And so how might we try and represent that using an approach kind of like nearest neighbor classification? Well, ideally, we need to extract some features out of emails that we can use to try and predict whether those emails are going to be spam or not. And there's a lot of different features we could try to capture, but some of them might be whether the person who sent the email is one of your contacts or not, whether there are misspelled words in the email, or the length of the email, or whether there are words in all capital letters, or particular keywords in the email that are often representative of spam email. And then you need to collect some data based on that. Look at a bunch of existing email that have been manually tagged by people as either spam email or not spam email. And then using that, you could imagine doing something very similar to what we've done here, but instead of plotting points that are either raining or not raining in space, we can instead plot emails in this multi-dimensional space where maybe the red envelopes represent spam emails and the blue envelopes represent emails that aren't spam. And you can imagine if a new email comes in, what does your email client do to try and assess whether it's spam or not? There are a lot of things that it could try to do, but if it was going to follow a nearest neighbor-like approach, then one thing we could do is extract those same features from that email, count up the misspelled words, figure out if the sender is in your contacts or not, and then compare it to other emails that are already in the data set to be able to say, what is the email that it is closest to? And based on that, or maybe if we're using k nearest neighbors, looking at the 5 or the 15 or the 25 emails that it's closest to, and use that to make a judgment as to whether we're going to predict that an email is spam or not. And once again, it might not get it right. It might be wrong because the features aren't quite right, or because we don't have the right data in the data set, or there might be emails that are similar where one is legitimate and one is actually spam. And that's something we need to just be aware of anytime we're using a machine learning model. We have to treat machine learning models a little bit differently than you would treat like a calculator, where if you type in a calculation into the calculator, you can be pretty certain that when you press the equal sign, the answer you get is the right answer. Machine learning models are trying to predict what the right answer is, but there's always going to be some amount of uncertainty, some amount of error that's going to be inherent in that process. And so we can't quite rely on the data in the same way that we could rely that the calculator is always going to be right. We can make our machine learning models better and better by using better processes for training them, giving them better and more data. But ultimately, we need to recognize and always be aware that there's always the possibility that they're going to produce something that is incorrect, and make sure that whatever processes we have for using these machine learning models is able to deal with that too. Nonetheless, nearest neighbor classification can still be a really powerful tool, even though it's not going to be accurate all the time, because it can often do a pretty good job of detecting whether something belongs to one category or to a different category. But as the amount of data increases, as the complexity of the data increases, and as we start trying to deal with more sophisticated patterns, ultimately, we might need more sophisticated tools as well for how we're going to go about doing our classification. And so then we need to introduce some other algorithms, some other ideas for how to engage in this classification process. And so here, we're going to introduce one of the most powerful tools in machine learning and one of the most versatile tools, and that is the neural network. And we're going to see what neural networks are, how they work, and how we can apply them to these kinds of prediction tasks that we've been looking at today. So neural networks are inspired by the human brain, that the human brain is made up of neurons that look a little something like this. And we have many neurons that are all connected to each other. And the idea is that these neurons are passing electrical signals to each other, that one neuron might get activated with electrical signal, and once it reaches enough electrical signal, it can then pass on that electrical signal onto another neuron, which might then fire and then pass on the electrical signal to a neuron after that. And so through these interconnected neurons that are passing electricity between each other, they can perform some calculations. They allow our brains to work, and they allow our brains to think. The idea then was to take the same idea and put it inside of a computer, to create not a biological neural network, but an artificial neural network, something that was structurally similar, but that a computer could use in order to try to make predictions as well. And so here is what we might represent as a neuron of an artificial neural network. We'll sometimes call this a neuron. Other times, it's just called a unit of a neural network. But this represents a neuron of the computer's brain. And you might imagine that they could be connected to some other neuron via connections that look like this, where one neuron could pass information to the neuron after it. And usually, each one of these neurons is going to be storing a number, because ultimately, computers are just reasoning and thinking in terms of numbers rather than any other concept that we might try to imagine. So each one of these is representing a number, passing along numbers along these connections to other neurons that might exist in that neural network as well. So how might we construct a neural network to try and solve these kinds of prediction problems? What might that ultimately look like? Well, let's start by looking. Sorry. OK, I'll go back a few. I'll start from artificial neural networks here. Yeah. So now what we might be interested in doing is building not a biological neural network, but an artificial neural network that can exist inside of a computer instead. And so here what we see represented is what we might call the neuron of an artificial neural network. It's often called a neuron, sometimes also called a unit. And the idea is that this is an artificial neuron that will store some number, because computers are ultimately storing numbers in terms of how they operate. And these artificial neurons can be connected with each other as well. So here are two different units that have this connection between them. And just like biological neurons can pass electricity from one neuron to another, these artificial neurons can pass their numerical values from one to the other. So whatever value this unit happens to be storing, it might then pass along to the unit after it. And neural networks have proven to be incredibly powerful tools for solving a wide range of problems in machine learning and artificial intelligence. And there are also a lot of different types and architectures for what neural networks can look like. But today we're going to start by looking at one of the earliest models for the neural network, something called the perceptron. And we'll look at how the perceptron model of the neural network could be used to try and solve a prediction problem like predicting whether or not it's going to rain. And so here's how a perceptron is organized. It starts with an input layer, just a sequence of neurons, where each one of these units represents some of these input features that we wanted to measure before. So remember, for example, if we were trying to predict whether or not it's going to rain on a particular day, we had 4 different features of interest. We had temperature, air pressure, cloud cover, and humidity. And each one of those is going to be represented by one of these units in this perceptron neural network. And what we're trying to do is we're trying to use these values to predict some output neuron. This is the output neuron of our neural network. That's going to represent whether or not it rains, where maybe a value of 0 means that it's not a rainy day, and a value of 1 means that it is a rainy day. So here's what our perceptron looks like. We have 4 units here, each one representing one of these input features, each one storing a number corresponding to that particular point of data. And we'll see how that's going to work in just a moment. And then all of these input units are connected via these connection lines to this output unit that ultimately is going to predict whether or not it's going to rain. You can think of this neural network as really representing a function. Remember, a function takes an input and produces an output. That if I give the neural network these 4 values as input to the network, what I want the network to do is, via these connections, calculate the value for this output neuron to decide, is it a 0, meaning it's not going to rain, or is it a 1, meaning that it is going to rain. And so once I've built the neural network, and once I've trained it, and we'll talk about the process for doing that in just a moment, the end goal is that I could just pass in values into the input layer, the neural network will do its calculation, and by the end, I'll be able to look at the output layer and say, is it a rainy day, or is it not? And so how is the neural network actually doing this calculation? How do we take these input values and transform it into something that can tell us if it's going to rain or not? Well, for now, let's abstract away the details of — sorry, there was a slide I didn't expect. OK. Where do I want to take this from? OK, pass it through the network in order to predict whether it's going to rain or not. OK, I know where to pick it up, but is there something should I walk or do something to make it easy to transition?
I feel like you've been at the TV for a while, right?
I think so, yeah.
So I guess I'd pick it up from the content points. It'll take a while for us to scrub back to wherever you just started from again. So as long as you're at the TV, we should be able to.
OK. OK, so we just talked about passing in the values into the input, getting the output to predict the 0. So what we're seeing in this case is that we've passed in 4 values, a value for temperature, a value for air pressure, cloud cover, and humidity, and the output is a 0, meaning based on all of this input data, we predicted that it's not going to rain. But if these values were a little bit different, you could imagine passing in different values for a different day, then maybe the neural network is going to calculate something different as a result. Maybe now it's going to calculate a value of 1, meaning that it is going to rain. So what we'd like to do now is understand how it is these connections are actually working. How is it that we're using these 4 input values to try and predict this output unit as a result of the neural network? So we'll get rid of the specific labels for what these particular features are, and we'll just replace these with variables so that they're a little bit easier to talk about. In this case, we have 4 inputs into our neural network. We'll give each of those variables a name. We'll call the first one x1, x2, x3, and x4. And then we have our output, the thing we're trying to predict. We'll go ahead and call that y. So what we're interested in doing is finding some way to combine x1, x2, x3, and x4 to be able to calculate what we think the value of y should be. Should it be a 1 or should it be a 0? At least for now, we're just going to consider those two binary options. It's either a 0 or it's a 1. And, well, one way we could do that, to combine a bunch of values, is by adding them all together. So that might be a place we could start. We could start by saying, go ahead and add up x1 plus x2 plus x3 plus x4. And then we need to use that sum to decide if this output unit should become activated or should fire or not, are both terms we use interchangeably for that kind of idea. And the way we might do that is by defining some threshold, so some number that's acting as our threshold. And if we add together x1, x2, x3, and x4, and it at least meets that threshold, then the output unit is going to become activated. It'll have a value of 1. But if the sum of all of these numbers is below that threshold, then the unit doesn't become activated. And so the output is going to be a 0 in that case. So that's how we might start by thinking about this. But one thing we might realize pretty quickly is that just adding together the numbers is a little bit limiting. It assumes that all of these values are equally important for trying to predict the output. And it also assumes that increasing any of these values makes it more likely that the output value will become activated. That increasing all of, for example, temperature and cloud cover and humidity and air pressure, all of those have the same positive effect on whether we think it's going to rain or not. And in practice, that might not actually be true. So what we need is something a little bit more sophisticated than just adding up all of the numbers unchanged to decide if the output unit is going to fire or not. So what we're going to use instead is that each of these connections is going to be associated with another number that we call a weight. So this is weight 1 here, here's weight 2, here's weight 3, and here's weight 4. And what the weights are going to represent is they're going to represent what effect each one of these inputs should have on the output. Because in practice, it might be different. The impact that temperature has on whether or not it's going to rain is different than the impact that cloud cover might have on whether or not it's going to rain. And these weights are going to capture that fact. And so what do we do with these weight values? Well, what we're going to do is multiply these values together. We're going to say, take x1, that first input, and multiply it by its corresponding weight, w1. Then we'll take the second input, x2, and multiply it by its weight, w2. And so you're seeing at the bottom here the expression for what it is the neural network is calculating. We're taking each of our values, x1, x2, x3, and x4, and we're multiplying them by the corresponding weight, w1, w2, w3, and w4. We sum all of those things up. Those weights could be big, they could be small, they could be positive, they could be negative, but ultimately they have the goal of calculating some sum, this weighted sum of all of these values. And usually what we say is that if the sum of all of those values is at least 0, so 0 or a positive number, then the output unit is going to fire. It'll have a value of 1. Otherwise, the output unit will have a value of 0. And so what should these weights be? Like, what should the weight be that we assign to temperature? And what should the weight be that we assign to cloud cover or to air pressure to decide whether or not it's going to rain or not? We as humans probably don't know. We don't know what the right values should be, but that is what the machine learning process is all about. If we give the neural network a whole bunch of data, we give it some values for x1, x2, x3, and x4, and we give it what the correct value of y should be, what the correct output is, did it rain or did it not, for example, then what machine learning is going to do is it's going to allow us to figure out what the correct values for these weights are going to be that allows the neural network to do a good job of trying to predict the output based on the input. And we'll see an example of that in a little bit. But when we talk about what machine learning is, we talk about the process that machine learning is the computer learning something. In the context of a neural network, what is it actually learning? What the neural network is learning is it's learning what the values for each of those weights should be. Those weights are what we call parameters, the particular things that the computer is learning when it's engaging in machine learning. And so when you give this neural network a whole bunch of data, we give it the x's, we give it the y's. What the computer is going to learn is it's going to learn these w values. It's going to learn these 4 weights or these 4 parameters to figure out how do you transform all of this input data into that output data y. Is it going to rain or is it not in this particular case? Just to add one other nuance to this as well, oftentimes when you see a neural network unit like this, it's being calculated based on a whole bunch of units. We'll also add one additional parameter that's not actually connected to any of these inputs. That additional parameter is often using the letter B. It's called a bias. And basically, that just allows us to add some additional value that gets tacked on to the end of this expression, regardless of any of the inputs. Because maybe sometimes we want to say that an output unit is more likely to fire or less likely to fire, regardless of what the values of any of these input units happens to be. And so that's what that bias there gets used for, too. Sorry, quick break.
That was really good.
So that's what a neural network really is. You can think of a neural network as like a function. A function takes an input and produces an output. And a neural network does the same thing. We provide some data to the network as input, and then it produces some output as a result. But unlike a function that you define yourself, where you have to decide exactly the details of how it's going to transform the input into the output, with a neural network, we have a trainable function. We have a function where we can provide some inputs and we can provide some outputs, and the neural network will figure out what the values of these parameters should be, what the values of all of the weights should be, what the value of the bias should be, in order to allow it to best make a prediction from the input to the output. So let's get a little bit more concrete with this and put some real numbers to it so you can get a better sense for how this calculation is actually working. We'll look at a very simple perceptron that has 2 input units and has 1 output unit. And again, these inputs are connected to that output. And each of those connections has some kind of a weight, some number describing the strength of the relationship between the input unit and the output unit. So here we have a connection with a weight of 1, and here we have a connection with a weight of 2. And remember that the output unit also has a bias, some additional parameter that's not connected to any of the inputs. And so let's imagine we have a bias of 3. And so this is a very simple neural network that has 2 inputs, and we're going to calculate 1 output. And we'll walk through the steps from beginning to end of what that calculation might look like. So let's imagine we provided some data as input to the neural network. We provided maybe a 4 for this input and a 5 for that input. And what we're interested in doing is calculating whether this output neuron is going to fire or not. Is it going to be a 1, or is it going to be a 0? So what's the math? How are we actually going to do this? Well, remember that each of these inputs, rather than just add them up immediately, we're going to multiply them by their weight first. The weight is going to represent what the relationship is between the input and the output. So we have our first input here, which is a 4. It has a weight of 1 in this connection to this output unit. And so we're going to multiply 4 times 1. That's going to give us the number 4. Then we're going to do the same thing with this other input. We have an input of 5 here, and this connection has a weight of 2. So we're going to multiply those two values together. 5 times 2, that's going to give us a value of 10. And now we're going to add up all of these numbers together. We're going to add together the 4, we're going to add the 10, and we're also going to add in this additional bias of 3. It's not connected to any of the inputs. We just add it every time. So we're going to add together 4 plus 10 plus 3. That's going to give us an output of 17. And what we're trying to do with this output unit for now is we're going to compare it against a threshold. By default, we use a threshold of 0. So we can say the number 17, is it at least 0? Is it 0 or greater? Well, it is. 17 is more than 0. So this output unit is going to fire. You can think of that biologically as like receiving enough electrical signal that it activates the neuron and causes it to fire as well. So this one is going to end up with an output value of 1. And so what we've just done is run this neural network. We've used the input, we've done the calculations based on all of the parameters, and we've calculated what the output should be. Let's try and repeat that same calculation now, but we use different values for the parameters. Instead of a 2 as the weight of this connection between the second input and the output, let's imagine the weight were something different. Imagine we used a weight of -2 instead. And now we'll repeat exactly the same math, given different values for the weights, but with the same input. What is the output going to be? Well, we start the same way. Take each of the inputs, multiply it by its corresponding weight. 4 times 1, that gives us the number 4. Now we've got 5 times -2. That's going to give us a negative result. 5 times -2 is going to give us -10. And now again, we add together the values, and the bias just gets tacked on at the end. It's not connected to any input. So we add together 4 and -10 and 3. And that's going to give us an output of -3 as the answer to that weighted sum. And again, we compare it against our threshold of 0. 0 is our threshold. If it's 0 or above, that means the output unit is going to fire. In this case, we ended up with a value of -3, which is too low. It didn't reach that threshold. So the output unit isn't going to fire, and it's going to end up with a value of 0. So depending on the inputs, we do this calculation, and we can decide, is the output unit going to fire or not? And so what we haven't talked about yet is how these weights actually get set. Because initially, if I just give you a neural network and tell you to run it, we don't know what the weights should be. The best we could do is just guess randomly at some weights, and it's not going to be doing a very good job of trying to predict the output based on the particular input. But what we're going to do is train the neural network. That is to say, adjust these weights over time by giving it some example data and having it learn from that data. So what might that look like? Imagine that this were some piece of data that we already had with an input of 4 and an input of 5 and some output. And imagine that the output in this case was wrong, that we predicted that the output was 0. But if you actually look at the data itself, the actual value should have been 1. We maybe thought that it wasn't a rainy day, when in reality it was a rainy day. So something is not quite right with the way that this neural network was calculating what the output should be. And what that means is that we really should make an adjustment to these weights. And so how should we adjust those weights? Well, in this case, let's think. The predicted value that we predicted was 0. The actual value was 1. So what would it have taken in order to get this output to be a 1 instead of a 0? Well, this weighted sum, the sum of all of these connections, needed to be higher. Because right now it was a 0, meaning it was too low, it didn't reach the threshold. If only that weighted sum were a little bit higher, then maybe it would have crossed that threshold, and we might have gotten the actual value of 1. So if we predicted a 0, the actual value should have been 1, then what we might learn is that these weights, in this case, need to increase. They need to increase in order to increase the value of this weighted sum to make it more likely that we get the output that we actually wanted. So we could then go ahead and take these weights, we could increase them all, and maybe now it's a little bit better at trying to make these kinds of predictions. And we'll repeat this again and again and again with different points of data to be able to make these predictions and see what should the correct value of the output be. And notice that we didn't change the weights by the same amount. We changed them by different amounts. We're going to adjust the weights more for the larger inputs. This 5 is bigger than this 4. So this 5 had more of an effect on this calculation process. And therefore, we're going to adjust it by more as a result. So we can tailor our adjustments to the weights based on what the particular values of these inputs happen to be. And so that's essentially what the neural network is doing. We're able to take these calculations, give the neural network some input. It's going to compute this weighted sum, decide whether it meets a threshold or not, and use that to determine what the output value should be. And depending on whether or not it's right or wrong, we can then train the neural network. We can modify the weights in order to figure out what the correct value of that output should actually be.
Can I interject with a question that
Yeah.
may or may not be excisable?
Sure.
Are these linear relationships between your x's and your w's sufficient to capture scenarios in which some of the inputs might cross some threshold that suddenly make it way more likely for the output to be 1 or 0? For instance, if it's suddenly greater than 0 degrees Celsius, it's way more likely or way less likely to snow. But if you're below that, it's very likely. So there's these interesting inflection points in the input.
That's possible. We're going to get to that later. Yep.
Then, yeah, let's not record that then.
Was that the only question, or was there another one?
That was it.
OK.
Actually, can I ask a clarifying question?
Yeah.
All of the example where you had a negative weight made sense, but in the first
So now we've seen what this looks like with a very simple neural network with just 2 inputs, 1 output, with numbers that we kind of made up ourselves. Let's now take a look at this in the context of a real-world data set. In the 1930s, there was a famous data set collected called the iris data set that looked at a bunch of different species of the iris flower. In particular, we're going to be looking at just 2 varieties of irises for today. And what this data set collected was information about these 2 particular varieties of iris flower and measured particular features of the iris itself. So what are the features in the data set? Well, what they looked at was they looked at the individual petals, and they looked at the length of the petal as one of the features. They also looked at the width of the petal as another feature. And then they also looked at the sepals, which are these green leaf-like parts of the flower that enclose the petals. They looked at the sepal length, and they also collected the sepal width. So we have those 4 values to work with: the length and width of the petals, the length and width of the sepals. And based on that information, what we'd like to do is try and predict what kind of iris is it. Between these 2 varieties of iris, which one do we actually have based on the values of the length and width of these various features of different parts of the plant? And so what might that look like represented as a neural network, as a perceptron-style neural network that we've been working with so far? Well, we have 4 inputs in this case, corresponding to the 4 input features that we've collected. We've collected 4 pieces of information about the flower. We've collected the sepal length, the sepal width, the petal length, and the petal width. And based on those 4 values, what we're trying to do is we're trying to predict an output. We're trying to predict what kind of iris it is. 1 will correspond to one of these varieties of iris, and a 0 will correspond to the other one. Again, we're making a binary classification, at least for now, where we're just trying to predict one of 2 categories. Is it 0? Is it 1? Is it one variety of a flower? Is it another? Is it above the threshold, or is it below the threshold in the context of what this neural network is ultimately trying to calculate? So that's the class that it's trying to predict. What kind of flower is it? And now let's look at some real data taken from this data set to see how this prediction process might actually happen. We need to start by giving the neural network some weights. And again, before we've seen any data, we have no idea what values these weights should be, so we can just start them randomly. We're going to pick random values for what the weights are, which means to start with, our neural network is not going to do a very good job of predicting what kind of flower we're working with. It's completely random, so it's as good as just making a random guess. But what we're going to do as we look at data is make modifications to the weights. The machine learning process is going to allow us to learn what the right values for these weights should be to allow us to predict, based on all of this input data, what the class of the flower actually happens to be. Remember that we also have this bias value as well. That's going to get added to this weighted sum. And we're going to learn that too. In the same way that we learn what the correct values for each of the weights should be by looking at the data, we're also going to make modifications to the bias. If it seems like the output neuron is firing too much, maybe we'll decrease the bias. If it's not firing enough, maybe we'll increase the bias. But that value too is also going to be learned every time we look at an example and learn whether we were right or wrong about that particular example. So here's our neural network, and here's an example piece of data. We've got the input features, the sepal length, sepal width, petal length, and petal width. And we also have what class it belongs to, which we're just deciding is going to be 1 or 0, depending on what kind of flower it happens to be. So this is an existing piece of data in our data set. And we could try our neural network out and see how it does. We could pass in each of those input features as inputs into this neural network. We could do the weighted sum calculation. Each of the inputs is going to be multiplied by its corresponding weight. At the end, we're going to add in this value of the bias. We're going to take all of that together, and we're going to see, is it at least 0 or is it not? In this case, it is at least 0, so we're going to get an output of 1. And we can compare that. We can now check our work and say, here's what the neural network calculated. It calculated a value of 1. Was it right or not? And we can look back to our original data. We can see that, yes, indeed, it was right. The class was 1, and that's the same thing that we predicted. So in this case, at least, we did a good job. But of course, purely by luck. We just guessed what we thought the weights should be, and in this case, we happened to get it right. We're not always going to get it right, though. Here's another example data point. This one looks a little bit different. It has different sepal length and width, different petal length and width. It belongs to a different class. And we can try the same thing again. Take all of those input features, pass them in as input to this neural network, and then perform the neural network calculation. Multiply each input by its corresponding weight, add all those together, add in the bias at the end, and figure out what we predict. Is it above the threshold or below? In this case, it'll end up being above 0. And so we'll end up getting a value of 1 as the output. And now when we check our work, we realize, we didn't do it right. We predicted that the class was going to be a 1. But if you look at the original data, the class is going to be a 0. And so we got it wrong. But this is something we can now learn from. We can say, whatever we just did, clearly something wasn't quite right. We ended up getting the wrong answer. And so what we should do is modify the weights so that we're at least closer to getting the right answer next time. And so how are we going to modify the weights? Well, in this case, we predicted a 1, but the output should have been a 0. That means the weighted sum that we calculated was too high. The weights were too big because it made the value too high. It caused the output neuron to fire. But the output neuron shouldn't have fired. It should have been a 0. And what that means is we need to decrease all of these weights. We'll probably decrease the bias too. But we're not going to all decrease them by the same amount. We're going to decrease them proportional to these inputs. So these bigger inputs, this 5.8, the 5.1, those were the more important values that contributed to this result that we just got. And so we're going to adjust those weights by more than the inputs that were less important for this particular example. So we'll go ahead and decrease all of the weights in this case. We get an updated set of weights, and then we can try again. We can try a new data point, see what result we get. If we got it right, great. If not, we can learn from that and continue to adjust the weights as a result of that. So if we repeat this process over and over, give this lots and lots of data, with every new piece of data we get, we have something we can learn from. We can learn, did we do it right? And if we did it wrong, we learn how to adjust the weights. And eventually, by doing that with enough data, we can arrive at some weights that actually do this job pretty well. They can take the input data and predict what the correct type of flower actually should be. And in some ways, this is kind of remarkable. We started from a completely random neural network, weights that we just decided on randomly that weren't doing a good job at all of deciding what kind of flower it was. But by making adjustments to the weights over time, little changes to what the weights are doing, in the end, we arrive at a situation that this neural network can actually do a very good job of taking the input and predicting what the output is going to be. So what is it this neural network is actually calculating? What kinds of things can we be learning? Well, ultimately, remember, what the neural network is doing is computing this formula. We're taking each of the inputs, which are our x values, multiplying them by weights, and then adding on a biased term at the end. So this is the math that the neural network is doing. And if you were to graph this visually, think, what does this look like? What the neural network is learning looks kind of like a line, at least in 2 dimensions. In 2 dimensions, you can represent what the neural network is learning as a line, where it's learning that on this side of the line, it's one kind of flower, and on that side of the line, it's some different kind of flower. This is what we call a linear combination of all of the input data. And that's what it would be in 2 dimensions. But as we've talked about before, as we have more inputs, in this case we have 4 different input features, you could imagine doing the same thing in more dimensions as well. It's just a little bit harder for us to visualize here. But there are some limitations here. That if we're just drawing a line, there are some relationships that we can describe, if there really is a line that cleanly separates one of the kinds of flowers from another. But there are other relationships that are a little bit harder to define in that same way. Let me give you an example. OK. Sorry, go back. We're almost done. All right, and we have a question. Yes.
Sorry.
Sorry.
I got to
All good.
mute this. Sorry, Andrew. Okay.
All right, and we have a question. Yes.
So how does the neural network know by how much to adjust each of the weights given this new set of data?
Yeah, how does the neural network know how much to adjust the weights every time it sees an example and it's trying to learn from it? Ultimately, what we're going to do each time we see an example and we get it wrong is we're just going to adjust the weights slightly to nudge the weights in the right direction so that hopefully over time, after lots of examples, it's going to do a good job of trying to predict the output based on the input. In practice, what programmers will do is usually they'll define some amount, some predefined learning rate, so to speak, that is the amount that we're going to shift the weights by, but we're going to do so proportional to the input, because every input's going to look a little bit different. Maybe in some of the inputs, the first two input values are larger, and in other inputs, the latter two input values are larger. And so depending on which were the more important input values for that particular example, we'll adjust the weight proportionally by more in those cases in order to try and nudge the neural network along in the right direction. So that's ultimately what's going on when we're trying to train the neural network. And the formula that it ends up calculating is a formula that looks something like this. We've seen this before. We're taking all of our inputs, all of these x values, multiplying them by the weights, these w values, and then adding on the bias term at the end to calculate what the end result is going to be, to determine if it's going to exceed that threshold or not. So what does that look like visually? Well, in 2 dimensions, we could try to visually represent this as a line in 2D space. That what the neural network is doing is it's learning by performing a linear combination, so to speak, of all of these input features, a line that separates that on this side we have flowers of one kind, and on that side we have flowers of a different kind. And in higher dimensions, you can imagine doing something similar. We've talked before about how we can visualize something in 2 dimensions, but a computer can do that in many more dimensions too. That in our case, we have 4 different input features, and you could imagine having a 4-dimensional space to represent what all of those look like too. We're just showing it in 2 dimensions visually for now, but it's the same idea if we were to move into higher dimensions too. And while this can often be useful, it's really only useful if we can cleanly separate our data in a linear fashion like this by drawing a line, where we could say, by drawing a line through the space, that things on this side of the line belong to one category, and things on that side of the line belong to a different category. But in practice, that isn't always going to be true. And we can take a look at an example, a fairly simple example, where it won't be true. Imagine that I have this data, where I have 2 red points, one here and one here, and I have 2 blue points. I have one here and then one in this corner here. Can you draw a line for me, a single line, that will separate the reds from the blues? And it turns out you can't do it. Like I could draw a line this way, but I got a red on this side and a red on that side. I could try drawing the line a little bit differently, but it's really no better. There is no one line that will cleanly separate the reds from the blues. And so we have a little bit of a problem here, that in the model that we've described, this perceptron that we've built, it can really only do things where we can draw a line and say things on one side belong to one category and things on the other side belong to a different category. But in the real world, data is often not that clean. It's a little bit messier. We're going to need some more sophisticated strategies for figuring out how to deal with it. So how could we do something like that? Imagine we have 3 inputs and we have 1 output, and we're trying to predict the output based on the input. Well, the answer is going to lie in adding more layers to the neural network. That so far we've had just 2 layers to our neural network. We have this input layer, and then we have the output layer, the thing we're trying to predict. What we're going to introduce now is what's called a hidden layer. The hidden layer exists in between the input and the output. And each of the units in our input layer is going to connect to each of the units in our hidden layer. And then each of the units in the hidden layer is going to connect to the output. And what each of the units in the hidden layer are going to do is they're going to behave similarly to the output unit in that they're going to have some kind of an activation function too, something that decides if this unit is going to fire or not. And by adding in that in-between activation function, the effect of that mathematically is it's going to allow us to break the linearity. It's not just going to be a line anymore. It can be a more complex shape that this neural network is calculating. And so we have more potential types of functions that we could model by trying to translate the input to the output. So let's talk about now what those activation functions really look like. So what we're going to try and do is decide on an activation function, which is to say, how should the unit decide if it's going to fire or not? With the output neuron we were just dealing with, when we had the simpler perceptron, our activation function was fairly simple. We had a threshold, and if it exceeded the threshold, then it fired and it activated with a value of 1. Otherwise, it had a value of 0. That kind of activation function is what we call the unit step function. Essentially, it's defined like this. If the input is less than 0, the output is going to be a 0. Otherwise, if the input is at least 0, then the output is going to be 1. And visually, if you were to graph the unit step function, it looks a little something like this. If you imagine this middle point being 0, anywhere to the left of the 0, it's going to have a value of 0. It's not activated. Anywhere to the right of 0, greater than 0, it's going to be activated. It'll have the same value of 1. And we could do that with our hidden units too, with these middle layer of our neural network that are performing these calculations. They could use this unit step function, but it might be helpful for our units to be able to represent multiple values, not just always be 0 or 1, but to represent a range of possible values, to represent more possible ways we might want to keep track of the input data. And so what's an alternative? There are a number of different options we could use for what the activation function looks like. But one that happens to be particularly popular is the rectified linear unit, or ReLU. And the idea there is that if the input is less than 0, the output is still 0. But otherwise, if the input is at least 0, the output is whatever the input was. And so that's going to look like this kind of a shape, where, again, if it's less than 0, the output is still going to be 0, a flat 0. But anywhere to the right of the 0, greater than 0, then as the input gets bigger, the output is going to get bigger too. And that's going to allow our hidden units to represent more possible values. And the important thing to see here is that this line is not just a single line. It's got a little kink in it. It's flat, and then it angles. And the fact that it's not a perfect line means that what this neural network can learn are things that are not just perfect lines. Whereas before, we could only do things that were perfectly linearly separable, so to speak. You draw a line through it, separate things on one side of the line from the other. Now we have the ability to represent much more sophisticated patterns in these neural networks that have multiple layers. So what other changes might we need to make to this neural network? Well, so far we've been dealing with neural networks that just have one output unit, where that output unit is a 1 or a 0, representing if it belongs to one category or another. And that was useful for things that are a binary decision, like is it going to rain or is it not? But sometimes we might have input, and we want to categorize it into multiple different categories, more than 2 different categories. Imagine we have more than 2 different species of flower, for example, and we wanted to decide which of 3 different kinds of flower is this particular input data, what does it belong to? And so how could you represent that in this neural network? One common way to do it is instead of having one output unit that's just making a binary decision, yes or a no, we'll instead replace that with multiple output units where there's one output unit for each categorization, each class that we want to group things into. So if we're trying to predict, based on input data, which of 3 different flowers a particular data corresponds to, instead of having one output unit, we might instead have 3 output units. And each one of our hidden units here is going to be connected to each one of these output units. Each one of these lines represents a different connection with a different weight. And each one of these outputs represents flower type number 1, flower type number 2, and flower type number 3. And once we get those output values, usually what we'll do is we'll reweight them so that they add up to 1, something like a probability distribution, so to speak, where we get like 0.6 and 0.15 and 0.25, where all of these numbers add up to 1. And what we can do then is interpret the output as some kind of a probability, where we can say, based on the output of this neural network, there is a 60% chance that the input data belongs to category number 1, a 15% chance that it belongs to category number 2, and a 25% chance that it belongs to category number 3. All right. I'll pick up from there with one last topic, and then almost there. So if we're trying to predict which of three...
I'm
Okay.
sorry. I
No
thought I
worries.
muted it.
You're clear anytime, buddy.
OK. So if we're trying to predict which of three different flowers the input data might correspond to, then instead of having one output unit, we might imagine having three output units, one for each of the different types of flowers: flower type number 1, flower type number 2, flower type number 3. And then for our hidden layer here in the middle, each one of these hidden units is going to be connected to each of the three outputs. And so when we perform this calculation, rather than get one output value, we'll end up getting three output values: one for a value for flower type number 1, one for flower type number 2, and one for flower type number 3. And what we'll usually then do with those values is that we will normalize them or adjust them to get them so that they all add up to 1. And then we can interpret that result as a probability distribution. In other words, we can interpret each one as a probability that the input corresponds to that particular output class. So in this case, we're saying that there is a 60% chance that the input corresponds with flower type number 1, a 15% chance that it corresponds with flower type number 2, and a 25% chance that it corresponds with flower type number 3. And so now that we have a neural network like this, we can see that there are many more connections that are going on here. We have this hidden layer where each of these hidden units has connections to each of the input units. Each one of those connections has a different weight. And likewise, there are different weights between each of these connections between the hidden units in this hidden layer and the output layer as well. And so when we're training this neural network, we're going to need to adjust all of those weights as we look at samples of data and decide whether we've done a good job of predicting the data, the output data, or not. And so what is the process that we can use in order to do that? We have a question first.
What do the units in the hidden layer represent, though?
Yeah, what do the units in the hidden layer represent? What these units in the hidden layer are going to do are they're going to represent calculations based on these inputs that are useful for trying to predict what the outputs are going to be. We, the programmer, don't really tell the neural network what these hidden units should be or what they should be calculating. The neural network is just going to figure out for itself what are useful things to calculate based on the input that are then useful for determining what the output is. It's essentially allowing the neural network, rather than do everything in a single step, to break things up into multiple steps, to be able to say, take the input and learn some intermediate representation that might be useful. They might not be understandable to us as humans, but they might be useful to the computer for then being able to say, what should these output values end up being? And so it's not always obvious to us what the hidden layer is doing, although we can look at the individual hidden units and try to understand, based on what they seem to be responding to, what it is that those units might be trying to calculate. Ultimately, what the neural network just needs to do is figure out what the values for those weights should be in order to get the hidden units to do something that ends up being useful. And the process they use to do that is something known as gradient descent. So what is gradient descent? Gradient descent is the process that we use in order to try and train a neural network, because we have a neural network that takes in some input, ends up producing some output, and when it produces the output, we then want to use that information, compare it to the original data, and modify the weights of the neural network in order to figure out how to get the neural network to be better in the future. So what gradient descent does is, after we run through the neural network, we get our output, we compare it to the original data, then what we're going to say is, for each of the weights in the neural network, what direction do we need to shift those weights in order to get the neural network to do a little bit better on that particular either individual piece of training data or a batch of a few pieces of training data. And then we're going to adjust each of those connections just by a little bit, to take a small step in the right direction towards trying to make the neural network more and more accurate. And so we run that through for some training data. We take a small step for each of the weights, make a small adjustment to them to try and make the network a little bit better. And then we try it with some new data, some different data. And then again, take all of the weights, make a small step in order to try to get them to more accurately reflect what the outputs ultimately should be. And by doing this one step at a time, we incrementally make the weights of the neural network a little bit better and a little bit better and a little bit better at determining what the output ultimately needs to be. And usually the way this happens is we get the output answer, we compare it against the original answer, and then we can say, well, for the weights that led up to these output units, how should those need to be adjusted in order to do a better job of trying to predict the output units? And then we can work backwards from there via a process known as backpropagation to then say, well, all right, once we've made the adjustments to these weights here, how do we need to adjust these weights between the input layer and the hidden layer so that the hidden layer can get a better representation for being able to then calculate the outputs too? And you could imagine extending this as we get more and more sophisticated machine learning models and neural networks, we're increasingly seeing networks with even more layers, and all of the weights in all of those layers are going to be adjusted slightly, little by little, until in the end, we're able to do a pretty good job of trying to make predictions. Yeah, question?
Is there always a linear relationship between the x's and the w's, such that you can't do x squared or x cubed?
Is there always a linear relationship between the x's and the w's? In general, for neural networks of this form, what each of the neurons is doing is it is just taking a linear combination of all of the inputs. So it's taking each of the inputs, multiplying them by a fixed weight. So if you want to represent things that are not perfectly linear, that are other types of functions as well, that's why you need the activation functions in the units to have something that is not quite linear. We saw that activation function before that was like flat the entire time, and then it sort of kinked up where it wasn't a perfect line. And that type of thing allows us to break out of just having linear relationships, and it lets the neural network learn other kinds of relationships between the input data and the output data too. But ultimately, it's going to depend upon what kind of data and how much data we have, what kind of structure is going to be most useful for trying to predict inputs and outputs. And one of the big themes that we're going to see is that while this is one possible design for neural networks, there are other possible designs too. And as we continue looking at machine learning and artificial intelligence, we'll explore other ways that we could have constructed neural networks in order to get them to be able to do a good job of trying to make predictions of output based on whatever those inputs happen to be. So a lot more still to explore. So we'll see you next time, and thanks so much for joining us.